So I'd like to talk to you about assembly language, and we're going to do a gentle introduction. Okay, so we'll start with the basics. I don't assume any prior programming knowledge, particularly, although just a very, very vague knowledge of programming might help. But we're not really going to make this technical at all. It's not going to be the nitty-gritty of specific assembler languages or anything like that. It's just going to be a general talk about assembler and a gentle introduction, especially for the lay person or someone who hasn't done much programming or any assembler before. Okay, so let's get started. So assembler is also known as assembly language, and it's a very low level language, very close to the CPU. It's very, the distance between assembly language and the CPU instructions, the native machine code, is very small. Okay, so it's very close to the computer's CPU, and it's very easy to translate assembly language into machine code, and that's the language that the CPU actually understands. So it's just ones and zeros. All current computers that we commonly use are binary, so ones and zeros are all a computer can understand. So assembly language is converted from our commands that we understand into machine code, which is ones and zeros, and it's a very easy process. A very small step is required. Okay, so they're very close together. When you think of assembly, you need to think about fairy steps. So doing things in little tiny steps. So breaking a great big problem down into very tiny steps and doing it with assembler that way. So you need a lot of assembler instructions to do what you can do, maybe with a few instructions in a high level language. Okay, so it's generally many instructions to get anything reasonable done. Many years ago I wrote tons of assembler code, and I really loved it. I love programming in assembler. I got really good at it, and I programmed it every day for a couple of years, and I really, really loved it. I'm very rusty now. It would be a lot of work for me to get back up to par again now, because you've got to keep a lot in your mind when you're coding with assembler. So you really need to get regular practice, and you really need to keep a lot of things in your head at once, or at least at your fingertips, to program in assembler. And to be a good assembler programmer, you need to get lots and lots of practice. Practice. Solve a wide range of problems, and pretty soon you'll develop lots of techniques and skills that will make things a lot faster for you. So your first program might take half an hour, your second program will probably take 5 minutes, and then after that you'll get much, much quicker. Okay, so you do get quicker. Okay, so what's a high-level language? We're talking about assembler versus high-level languages. What's a high-level language? And that's an English-like language, or programming language, such as Java, C, C++, Basic, Python, Perl, Ruby, JavaScript, Eiffel. All of those languages are all high-level languages. Okay, there's millions out there, hundreds of thousands anyway, and the most common ones are C and Java and Basic and Python and things like that. So in contrast to high-level languages, assembler executes very fast. Generally, if you want something done super fast, you do it in assembler. Assembler program compared to a high-level language program, when compiled, the executable program size will be much smaller with assembler. Hasn't got any overhead or as much overhead as a high-level language program might have. It's got smaller memory requirements in general, and it generally takes a lot more instructions. In other words, lots of lines of code to get the same job done. So you're generally writing a lot more lines of code when you do assembler compared to a high-level language. It requires programmers to keep a lot more information in mind and or at their fingertips when they're programming in assembler. There's so many things you need to remember. You need to remember what you've stored where and where it's stored and how it's stored and what data type it is and what you've got on the stack currently, and all sorts of things you need to keep in mind, and what the opcodes are to make instructions work and interrupts and things. Yeah, it's a lot of information to keep in your mind. And it requires more data shuffling, moving data in and out of CPU registers, on and off stacks, and so on as well. So when you're writing an assembler, a fair chunk of your code is going to be shuffling data around so that you can get access to registers. We've got examples of all of these coming up. Don't panic. Some tasks that are really quick and easy to do in a high-level language, such as Java, C++, Basic, Python, and so on, they can be very difficult. They can take a lot of extra work, and they can take a lot more instructions when you do them in assembler. Okay, so at least until you're an expert assembler programmer with a great library of routines built up, generally speaking, it's going to be more difficult more work, more lines of code, and more instructions when you do it in assembler. Some examples of those things that are really difficult to do in assembler: user input even is quite difficult, output to the screen, file I/O, database I/O, networking, game controllers, graphics, animation, all that sort of stuff's more difficult in assembler, at least until you get up to speed. Okay, and then by then you will have built up your own little libraries and routines which you can use, and then things become much quicker, much quicker. Like everything in life, practice makes perfect. So it comes down to getting practice. Practice. Every day, solve problems, solve a wide range of problems, and you'll get very good at assembler within a fairly short time if you put enough practice in. So get lots of practice writing assembler and you'll soon develop good skills. Okay. You don't have to be a technical genius. You don't have to be a maths genius. You just have to think logically and approach problems one step at a time. That's all you really need to do. So there are various types of assembler. All assembly languages share the same characteristics. They're small, fast programs, work with the registers. The command sets are basically similar in a lot of ways, but the commands may vary, and the number of commands may vary, and the power of the commands may vary. So every CPU has its own flavour of assembler, and that means it's got different instructions, different ways of working, different opcodes, different interrupt codes, all sorts of things are different. But the basic style of assembler, the basics of assembler are pretty similar across all CPUs in broad terms. Even with PCs, where you've got Intel CPUs, then there's a range of assemblers depending on the operating system and the CPU model you choose. So the good old x86 DOS assembler, which I loved programming in. That was my baby. I did a lot of work in that. I did a little bit of work in Windows 32 assembler, which was much nicer than DOS assembler. And as CPUs have evolved and more features are added, like the Pentium 3 and the Pentium 4 and the Core 2 and all that sort of stuff, every CPU Intel generates or releases has more instructions to do things. Like the latest CPUs have a lot of multimedia extensions built in and all sorts of things. So in the old days you had to program those yourself or use a library. Now they're often embedded in the CPU, ready to use. So so more instructions are being added all the time to CPUs. So a bit on registers and instructions. These are two things you need to keep in mind. So registers are small, super fast areas of memory in the CPU. Generally you've got maybe 16 registers or 16 areas where you can store data. It might be 8 registers. It depends on the CPU, depends on the architecture. Okay, but there are a limited number of registers. And then you've got instructions. And instructions are little commands that basically work with registers or mostly work with registers. And for example, to use instructions you usually need to move the data that's required into registers so the CPU can do its work. So if you've got data in main memory in your machine, you need to get access to that inside the CPU, and you move the data into the CPU's registers, or at least the memory address of the data, so that the CPU can then start working with the data. In general terms, here are some basic instructions. So we'll go through some basic ones. And again, these might look a little bit PC-like, but I'm not trying to base these on any architecture. So if anyone says in the comments, oh, the PC needs this operand on for that, I don't care. These are general purpose. It's just a general discussion. I'm not talking about the detailed nitty-gritty of a PC or 68000 or 6502 or anything like that. I'm just talking in general terms. Okay, so generally there's a move instruction, and that copies data from somewhere to somewhere else. And you've got an add instruction, which means add or increment some sort of memory address or value with some other value. You've got CMP, that means compare. You're comparing two values or two whatever locations. The jump command is like go to. It just jumps to another location in your program. Jump if not equal to. Jumps if the result of the previous compare instruction was not equal to. So the idea is you do a compare and then you do some sort of jump command, like jump not equals and so on. And there are various flavours of that. There's jump less than or equal to, JLE, and that jumps to another location in your program if the result of the last compare operation was less than or equal to. And as you probably guessed by now, there's many flavours of this. There's jump if less than, jump if greater than, jump if greater than or equal to, and many others. Jump if zero, jump if not zero, all sorts of things. Okay, so you do a compare, then you do some sort of jump if you want to. If you want to branch to different processing depending on what you're trying to do. Okay, lots of examples coming up. Don't panic if this is confusing. And then you've got push and pop, and that's to work with stacks inside the CPU or inside the machine, and many others. So there's many instructions. I've just talked about a few of the most common ones. Okay, so there's many others. Some instructions require specific registers, so they can only work a certain way with specific registers. So what you might have to do, if your program is using those registers for other things, then you might need to move or copy the data out of those registers, perform the instructions that require those registers and get them to do their work, and then move the data back in to those registers so it's back how it was before you did the instructions. Okay, and that's sort of a common thing to do with assembler. Because there's so few registers inside the CPU, things quickly become complex and may be hard to manage, so you've got to keep a pretty good logical track of what's where and what's being used for what. And you often need to use the data stack, for example, to push data onto it and then pop it off it again later on. So a lot of your assembly code could be pushing data onto stacks and popping data off stacks again later. Let's look at some examples. So I have the high level language over here, and it's going to be just the general language, not even a programming language. It's going to be more like pseudo code. And then we'll have the assembler equivalent up here over here. So let's look at a high level language, and I'm going to count the number of voters. So int voters is equal to 0, no voters so far. And I've got an age, and I'll get the age input from the user or from a file or from somewhere. And then if the age is greater than or equal to 18, then I'm going to add 1 to the voters. Voters equals voters plus 1. In other words, you're old enough to vote. So I'm assuming 18 is the voting age in this example, but that might vary depending on the region. So voters equals voters plus 1. And then whatever else you need to do, generate a report or loop through and get some more data or whatever you want to do. Okay, but I'm just focusing on this part of the code. Just these 2 lines of code I'm focusing on. Okay, so here's the assembler to do that. Okay, so we're going to move 0 into R9. R9 is going to be our number of voters. Okay, so we've got to remember in our mind that R9 is our number of voters. It'd probably be a good idea to put a comment over here next to it. R9 equals number of voters. And then so on. And then somewhere you're going to say move R1 to 18 to R1. So move the value 18 into R1. And then we compare R2, or move age into R2. So whatever value age is, I'm assuming it's from a variable or somewhere in memory. Move the value of age into R2. So R1 now contains 18, which is our threshold. And R2 contains the person's age. And we want to compare the two. Compare R1 and R2. And jump if less than, or actually that should probably be a jump if greater than, because it's comparing R1 and R2. If R1 is less than R2, it would be less than. If R1 is greater than R2, it would be greater than. And then add 1 to R9, so R9 is our number of voters. And then we've got a skip add down here. Okay, so jump if less than to skip add. So in other words, if R2, which contains the age, is greater than or equal to 18, we're going to add 1 to it. And if it's less than, we're going to jump down here and not add 1 to R9. Okay, so just this little bit of code here, maybe 5 instructions or so, is replacing 2 lines of code in a high-level language. And we've not even got into how to declare integers and how to do things like that yet. So we're just working with the very basics here. Okay. Another example, let's total the numbers from 1 to 10. So we're going to add 1 plus 2 plus 3 plus 4 and so on. In a high-level language, you declare some sort of total and set total equal to 0. And I've got a sort of a little like basic here. If you've done some basic, for count equals 1 to 10, step 1. So we're going to increment by 1. So we're going to go 1, 2, 3, 4, 5 each time we go through the loop. And total equals total plus count. So every time we go through the loop, we're going to add whatever the current value for total is onto count. So the first time through, total equals 0 plus 1. And the next time through the loop, total equals 1 plus 2, which is 3. And then the next time through, total equals 3 plus 4. Or 3 plus 3, which is 6, and so on. Okay, so we're just looping through there, and so on. So I'm just focusing on that little bit of the code again. I'm not getting how you declare integers and all that sort of stuff. That's a topic for another lecture. Okay, so in assembler, we're going to move 0 to R1. So R1's going to keep track of our total. And we're going to move 1 into R2. So R2 is our little counter. That's count here. That's R2. And then we're going to do add, which is just a little label that we add to our code, which is skipped by the assembler unless you've got an instruction to jump to that location, and the assembler jumps to that location. Compare R2 and 10. So is R2, in other words, our counter, equal to 10 yet? And jump if greater than to finished. So when it's greater than 10, we're going to jump to finished. Add R2 onto R1. So the first time through, we're going to add 1 onto 0, which is going to be 1. So R1's now got the value of 1. Add 1 onto R2. So we're incrementing our counter. And then jump to do add. Jump back up here again. Compare. So R2 is now 2. So compare R2 to 10. And it's not greater than. So we're going to add 2 onto R1, which is 1 plus 2 is 3. So now R1's got the value 3. Add 1 onto R2, so R2's now got the value 3. Jump back again, and just keep going round and round this little bit of code here until you're finished. Until this jump greater than fires off. And then finish is just down here, another label, and whatever you want to do when you've got the total printed to the screen or whatever. Okay, so here we've got maybe 3 lines of code, and we've replaced it with maybe 6 or 7 lines of code in assembler. So there's generally more lines of code in assembler. Short little fairy steps is what you need to think. Break a problem down and do it in tiny pieces. Let's do another one. Let's assuming you're using some commands that require certain stack variables, but you're using them for storing other stuff. Then I'll show you how you can preserve data onto the stack and then get it back off again. So in assembler, I'm going to preserve the register values I want to keep. And I push them onto the stack, so it's just a push command, push R9, push R1, push R7. So all of those values are pushed onto a stack. It's just like a stack of paper, and you're just piling pages on top of each other. Okay, the first one on the stack at the very bottom will be the value of R9. The next one on the stack, the second from the bottom, will be the value of R1. And the third one on the stack, the third one from the bottom, will be the value of R7. So it's just like a stack of paper, three pieces of paper in a stack with those values written on it. Okay, and then I'll do whatever I want with those registers. And then when it comes to time to restore those registers again, then I need to pop the values off the stack. And note that they come off in reverse order. Stacks, the last thing you add onto a stack is the first thing you pop off. Okay, the first thing you retrieve. So they're like a stack of paper. To get to the fourth item down in the stack of paper, you've got to remove the top 3 to get to it. Okay, so just keep thinking about stack of paper. So we pop them off again, but in reverse order. So R7, R1, R9, which is the reverse of the order I pushed them on. Okay, and that will restore those values back to the original values they had before whatever happened in here happened. Okay, so that's how you do it. It's not real hard. You'll just find yourself writing push pop a lot in your code. Let's do another example. Hello world, probably the simplest program people usually start with when they're writing a program in BASIC or C++ or Java or whatever. They start with hello world. So just in general terms, that's the sort of command you're looking for, print hello world. That's a sort of basic-ish sort of command. In Java, it looks a little bit different. System out, print line, hello world. In C++, it's a little bit different. You use C out or character out with some double less ends to pipe the data out to the device. With a new line at the end, hello world followed by new line. Okay, so that's how you do it in Java, but we're basically looking at this line of code here, just in general terms. So how do you do that in assembler? Okay, now I'm going to show you a PC-DOS assembler, which I used to do a lot of programming in. I used to love it, and I'm very rusty now. I'd have to go back to the drawing board virtually to start again now, because it's a lot to remember. But anyway, here's this. I just wrote this code before I put these slides together, so I'll show you the code for printing hello world in assembler. So you move the... so there's a message down here, we'll get to that. And you move the address of that message or the location of that message into DX, the DX register. Sometimes you'll see it written as load address, load address. But whatever it is, DX contains the data you want to print to the screen. You move the value 09 in hexadecimal, you move that into the register AH, and then you call interrupt 21. Okay, and interrupt 21 says what value has DX got, what value has AH got, what value have other registers got, and it does whatever values it's been told to do. So it says DX has got a bit of text data, pointing to some text data, AH at the value 09. So when I do interrupt 29 or 21H, the CPU knows that I'm printing data to the screen. Okay, and then if we move 4C in hexadecimal to AH, so 4C is a hexadecimal number, and then we call interrupt 21H again, that means terminate my program. Okay, and then the only thing we're missing is message. So this is whatever I wrote there, that's what it is here. Message, you could call it hello world as one command if you want to, and hello world up there if you want to do, that would be fine. DB means it's a data variable, okay, or data area, data buffer, and it contains the characters hello world, followed by an ODH, followed by an OAH, followed by a $sign. Now $sign means the end of input, the end of the data that it's going to print. So this interrupt 21H, when it's got a message address and AH has got the value 09H, it just keeps printing data until it runs into a $sign. Okay, so we're going to see hello world. ODH is 13 in decimal, and that's the carriage return, and OAH is 10 in decimal, which is the line feed character. Okay, so it's going to put hello world followed by a carriage return and line feed, which is basically what the print line does, and that /n there does. Basically the same sort of thing. Okay, so yeah, you can see there you've got to keep a lot in your mind. You've got to keep in mind when you're writing assembler what registers you need to set up with which values when you do things like display things to the screen or when you exit your program. You need to keep all these things in mind. There's a million and one things to remember, but I've got to tell you, it's a lot of fun. And if you like programming, you'll love programming in assembler, the chances are. And I certainly do. I used to do a lot of it, and I miss it. I do miss it. And this little example here's brought back all sorts of memories, as even though it's about the simplest hello world program you can write in assembler. It's still a fair bit of code compared to just print hello world. Okay, so where next? So if you're keen to explore further, what I recommend is you grab a good introductory assembler textbook or book for whatever CPU you have or whatever CPU you want to program for. If you've got a Raspberry Pi and you want to write some assembler for that, grab a Raspberry Pi assembler book or whatever. And that book will probably come with an assembler, maybe on a CD or maybe on a website. For the book, you'll be able to grab an assembler that they recommend and that they use throughout the book. And that would be a good way to go, because then the assembler you're using is the one supplied with the book. So that's good. Or else you can grab an assembler, and there's many are free and some are free and open source as well. So do a Google search and find an assembler. NASM's a good one, NASM, NASM. There's many videos out there on YouTube for tutorials and getting started and all sorts of things. So do a search on YouTube. And if you get into it and start doing things, just practice, and pretty soon you'll get really good. Okay, it'll only take maybe a few weeks, and a lot of it will become second nature to you. And I'll also add some links into the description. So some good assembler resources I'll add into the description below the video. So just check the description. And hope that was useful. That's my quick introduction to assembler. I hope that was useful. It's not really a scary language. Once you get into it and start writing a few little programs, pretty soon you'll become unfrightened and unscared. Okay, so have a try and see how you go. If you wondered about exploring assembler, and it's a rainy day, why not give it a go? Okay, hope that was useful. Thanks for watching. If you like the video, please give me a thumbs up. And if you want to keep track of my future videos or whatever, click the subscribe. But thanks for watching.